Hello. So, rejoice. This is the last video on thermochemistry, at least for college chemistry 1. Okay? We are going to see forms of calculating the change in enthalpy of a reaction. We did see calorimetry before, and when you have regular enthalpies, we are going to be talking about enthalpy of formation. Hess's law, this is going to be where we're going to use the things that I told you. This is not just a casual comment. Remember, when you reverse the direction of the reaction, I said you change the sign of the enthalpy. When we multiply an equation times a particular factor, you have to multiply times the same factor, the energy and all of that. And I told you that was important. It was going to be very useful later on. This is when we're going to be using it. And we are also going to see how to determine the change in enthalpy by using bond energy. So these are all going to be ways of determining enthalpy of reaction, putting to use what we have learned so far. Like I said before, we are not going to get all the way to the end. The final goal is to determine if a reaction is spontaneous or not, and we'll see that in college chemistry too. I hate that they split the chapter in two. Wish we could just do the whole thing together. But we're going to define the standard enthalpy of formation. Remember, the standard just means we're using standard conditions. So this is the enthalpy change for a reaction in which you produce 1 mole of a pure substance. So for instance, the enthalpy formation of carbon dioxide is this. Why? Because you have that energy that's been released there. If they ask you to write an equation, basically you have a carbon reacting with O2, but that is the change on enthalpy forming carbon dioxide. If you have an element, the element is already formed. Okay? So under standard conditions, the enthalpy of formation of an element is going to be 0 because you don't form an element. You don't form carbon. You don't form oxygen, but you do form carbon dioxide. Okay? Basically, this seems silly, but write the equations formation. Basically, you're forming them from constituent elements. So you want to form alcohol. This is not the way you make alcohol in the lab, but in theory, you could write you need 2 carbons, you need 3 hydrogens, you need 1 oxygen atom, so have an oxygen molecule. A calcium phosphate, again, you need 3 calciums. It just writes the equation from the elements that form them. Okay? I don't think anybody's going to ask you that, but we will be using here. So this is the important thing, Hess's law. Sometimes you can determine experimentally the enthalpy change in a reaction, like we did in the previous chapter. But sometimes you can't, for whatever the reason. There's a million different reasons why you cannot do it. So what Hess said is that if you can split a reaction into several steps, and he didn't say they have to be real steps, he didn't say they have to happen, but if you can on paper divide into steps and you know the enthalpy change for each one of those steps, you can add them up all together and that will give you the change of enthalpy for the reaction, because remember, enthalpy is a state function, so it doesn't matter how you get there. So you can come up with hypothetical steps. Let's say that you're trying to figure how you go from A plus 2B to 2D. And you say, for whatever reason, I cannot measure, but I know that A plus 2B from an intermediate compound C, and I know the change in enthalpy. I know that C is going to split into 2Ds, and I know the change in enthalpy in here. So if I add them up, notice that C cancels out, and I say A plus 2B comes to D. That was the original reaction that you had in there. So I can add up the 2 enthalpies. Obviously, some are going to positive, some are negative, depending was endothermic or exothermic. But this is a very common method of determining enthalpy for an equation when you know the change in enthalpy for steps. And like I said, let me insist, it doesn't mean that this reaction takes place in 2 steps. It means you can write it in 2 steps. Okay? But the steps are going to be given to you in every example, so you don't need to worry about inventing something. This is just an example of how this really works. You're trying to form carbon dioxide. This is the one-step equation. You can measure it experimentally, minus 394 kilojoules, because the heat is released. Or you can follow Hess's reaction and say, I'm going to divide into 2 steps. First, I'm going to make carbon monoxide, and then carbon monoxide is going to turn to carbon dioxide. And I do have the enthalpies for these 2. So when you add them up together, you say, okay, I have carbon monoxide and carbon monoxide, they cancel out, and 2 1/2 oxygen and 1/2 oxygen is going to form 1 oxygen. This equation is identical to the first one. That is the key. Whenever you're using Hess's equation, whenever you add up the equations, compare. If they're identical, then you can add up these numbers. And guess what? When you add them up, 394 kilojoules. This is just an example where it shows you that doing it in 2 steps gives you the same result that if you experimentally measure a 1-step reaction. Okay? This is just kind of proof that this system works. This is just the same thing I just went through. So let's look at an example. And I did pick probably a complicated one, but let me put it, this is the most complicated you're ever going to find. Most of the examples you're going to find in exams are going to be simpler than this. But you have this equation, the one that changes in enthalpy, for whatever the reason you cannot determine experimentally, but they say use these reactions in here. Because we know they change in enthalpies. And you start looking at them and saying, yes, but there is a problem because, like, for instance, fluorine here. Here's a reactant, but here's a product. And here you have 1 mole, and here you have 2 moles. So we're going to have to change that. And the trifluoride, here's a product, here's a reactant. So we're going to have to switch that. And the monofluoride, you need only 1 mole, and here you have 2 moles. So that's what I mean by you're going to have to rearrange these equations. And this is why I was emphasizing it was so important. If you want to reverse the reaction, where the reactants become products and the products become reactants, you have to change the sign of the change in enthalpy. If you want to multiply or divide times a number, you have to multiply or divide times the same number, the change in enthalpy. Okay? If you remember that, this is extremely easy. And I always tell students, start with the first one and find out where it is, and then you see what you need to do. Like, this is the first one. Okay, it's in the right position, but it has the wrong number. And you take all of the chemical reactants. So we say for this one, the problem that we had is that we need half. Remember, you have 2 monofluorides, but the actual reaction has only 1. So we're going to divide everything by half. If we divide everything by half, you have to divide the enthalpy. It's the same sign, just divide by half. Now we say fluorine is a reactant, and we go in here and it's a product. So we are going to reverse the order, which means we reverse the sign. Also, you have 2, and here you only want 1, so we are going to reverse the order and divide by 2. Okay? So we reverse the order, we change the sign, we divide by 2, so we divide by 2, and that gives us the new enthalpy. For the trifluoride, you say, okay, the only problem here appears a reactant, but it has to be a product. We reverse the order. When we reverse the order, what happens? You change the sign. So we have modified all 3 equations. Let me write them all that together now. These are the modified equations. These are the new enthalpies. And now you have to add them together. So you start looking and you say, okay, I have half an oxygen, and here I have 1 oxygen, so they cancel out. Okay? And here I have 1.5 difluorides, and I have 3 halves, so that's 1.5. So these ones are going to cancel out too. Okay? I didn't cancel that one. And yes, and half a chloride. So basically, when you cancel out things, look at this equation you come up in here and go back. You have the monofluoride plus fluorine gas to form the trifluoride. Go back to the original equation, monofluoride plus fluorine. You see, this equation is identical to what you got in here. If it's identical, it means you can add up these numbers, and that is a change in enthalpy. If they're not identical, it means either you made a mistake someplace, go back and double check. Maybe you need to do one more step. Maybe you did one step too many. That's why I say go back and try to figure what you did. But if this equation does not match the original, your answer is wrong. Try again. If it matches, then all you have to do is add up 3 numbers, and that's your answer. So this is a case, like I said, this is probably the most complicated because we are dividing twice, we are changing the order twice. There's one case where we both divide and change the direction of the reaction. This is probably very complicated. Most examples you're going to do will be easier. If you can do this one, you can do any. Go slowly. And once again, I have a worksheet where you have several examples for you to practice. Because once you get the idea, this is actually extremely easy. Okay? You can use that also with enthalpies of formation instead of, these examples here were just enthalpy for reactions. You can use the enthalpy of formation. Basically, what you're saying is that when you have a reaction, you have to break down the reactants. Okay? And the enthalpy of formation tells you how much heat you have to give to break the reactants. And then you're going to make new products, which means it's going to release some energy. That's enthalpy of formation. So you could do it making a bunch of equations, like Hess equation is probably going to be time-consuming. Someone simplify this, and it's going to make your life much easier. This equation rearranges everything in a very easy to remember, because yes, you do need to know this formula. Okay? But says that the change in enthalpy of the reaction is the sum of the enthalpy of formation of the product times the number of moles. Remember, this enthalpy of formations are kilojoules per mole, so you have to multiply times the number of moles, minus the sum of the enthalpy of formation of the reactants, again multiply times the number of moles. And if you have difficulty remembering this equation, I always tell the students products come before reactants alphabetically, so they come also before in the equation. But I would say 99% chance you're going to have to memorize this equation. I doubt it will be given to you. So we have an example here. Okay? So you have nitrogen dioxide and water react to form nitric acid and nitrogen monoxide. All of the enthalpy formations are in a table. So you use the equation. So you look at enthalpy formation of the products. Which are the products? Nitric acid. How many nitric acids? 2. So you have 2 nitric acids. This number comes from the table. Okay? There's another product, nitrogen monoxide. There's only 1, and this comes from the table. Minus. And I do put everything in brackets because we are going to put all of the reactants and all of the products. Okay. The reactants, you have nitrogen dioxide, and there's 3 of them, and the number comes from the table. And water, there's 1, and this number comes from the table. That's the answer. Very easy. The only thing that I can tell you is, well, 3 warnings, 3 problems that the students usually have. Remember, it's products minus reactants. Remember to multiply times the number of moles. And that should be easy if you write it because it's kilojoules per mole, kilojoules per mole. You want the answer in kilojoules. Okay? And be very careful. Sometimes you have like nitrogen monoxide, nitrogen dioxide. Make sure you read the table correctly, okay? I had the students putting the wrong number. Well, what can I say? I mean, the table is correct. If you cannot tell the difference between nitrogen monoxide and nitrogen dioxide, just slow down, okay? And don't forget these brackets, because if you don't put the brackets, you'll be adding this one, but you're actually subtracting all of the reactants. So calculate the number within the brackets and then subtract. It's easy. Like I said, the most common problem is whenever you have two molecules that are similar, write down the wrong number. That's where going slowly will help you tremendously. Okay? Now we can use also bond strength. When you have a covalent bond, and we'll talk about ionics in a moment, the energy to break a bond is called the bond energy. Okay? So we can use bond energies to calculate, maybe it's not very accurate, but you can calculate enthalpy changes because you're going to be breaking bonds, and we're going to, obviously not all of the bonds are broken in a chemical equation, but to make sure you don't miss anything, we are going to break every single bond in the reactants, and then we're going to form every single bond in the product. When you break bonds, that's energy you're adding. When you're forming bonds, energy is being released. So some are going to be positive, some are going to be negative in there. The overall value will tell you if it's exothermic or endothermic, depending where you come, positive or negative results. Exothermic, remember delta H is negative. Endothermic, delta H is positive. And depends which bonds are stronger, the bonds in the reactants or the bonds in the products. There's only one problem to this. How do you know the bonds? Well, the only way you can tell which bonds are going to be broken and which bonds are going to be formed, you need to know the Lewis structures of the reactants and the products. Remember, I warned you when we did Lewis structures. This is the gift that keeps on giving. You're going to need it later on in thermochemistry. Well, this is the later on. If you didn't do good in the exam with Lewis structures, or if you don't remember, go back to the video on Lewis structures, okay, and review it. Because if you don't have the Lewis structures, how do you know which bonds you're breaking? How do you know which bonds you're forming? If the Lewis structure is wrong, you're going to come up with the wrong answer. So very, very important. If you're not confident, go back and review Lewis structures. Again, this is summarized. You take the energy on the bonds that are broken, those are positive numbers, and you're going to subtract the energy of the bonds formed because that energy is going to be released. Those bonds in the table, they are always positive. Okay? So since the bonds formed release energy, that's why we put minus. But this equation, again, you need to know. And once again, you need to know which bonds are broken or formed, how many, and the only way you can do that is using Lewis structures. So here you have a table that will probably be given to you, okay? Nobody will expect you. Remember that I told you in the previous table, be very careful, don't confuse nitrogen monoxide with nitrogen dioxide. Here, when we talk about bonds, there's another thing you need to watch out. Look, for instance, the carbon-oxygen bond, you can have a single bond, a double bond, or a triple bond. And remember, a double bond is not two single bonds. A triple bond is not three single bonds. Okay? So write the Lewis structure and not only mention which bond between which atom and which atom, but it's the single bond or a double bond or a triple bond, because many times you're going to have a choice. Make sure you put the right number in the right place. Okay? All of the information is there. All you have to do is put the right information in the right place. Slow down. You have time. Okay? So let's look at a very simple example. Okay, methane, you can break it down to carbon and hydrogen. So what bonds do we have? Well, in this particular case, the only bonds that we are breaking are the carbon-hydrogen. There's 4 of them. You look in the table, one is 415 kilojoules per mole. You multiply times 4 moles. So that's the energy it takes to break a molecule of methane. You're not forming any bonds in there, so that's the end of the story. Let's look at a better example. Carbon monoxide plus hydrogen to form methanol. Okay, you write the Lewis structures, and if the letters and the numbers don't look the same font is because I had to copy them from different places. But anyhow, here you have carbon monoxide, has a triple bond, 2 hydrogens, a single bond, and this is methanol. You have this. So what do we say? It's going to be bonds broken minus bonds formed. Which bonds are broken? 1 carbon triple bond oxygen. So you look it up in the table. You break 2 hydrogen single bond hydrogens. You look at the table, 2 times that number. Now you subtract the form. What is form? Well, we have 3 carbon hydrogen single bonds. Let me just put this, the carbon triple bond oxygen. This is the hydrogen hydrogen. This is 3 carbon hydrogen. Then you have a carbon oxygen. And you have an oxygen hydrogen. Do the calculations. Oh, it happens to be negative, so obviously heat has been lost in there. Again, be very, very careful. When you're looking at this one, it's a triple bond. So don't give me the heat from a single bond. You have to look up in the table what is a triple bond. Don't forget to see how many bonds. You have 2 bonds in there. You have 3 bonds in there. So multiply times the number of bonds. Slow. You'll do it right. Okay? Don't rush. This is not the kind of problem you want to rush because it's so easy to make a silly mistake and get ruined when you actually knew the chemistry good. Now, when we talk about ionic bonds, remember we don't have a molecule. We have a lattice. So the energy involving a lattice is called lattice energy. And this particular book defines it as energy required to separate 1 mole into this component. But there are books that says actually the energy released when you form 1 mole of the lattice. Okay? Be very, very careful which definition your book uses because that can sometimes lead to confusion. But come to this book, we are breaking down this ionic compound into the separate. And obviously, when you're separating them, it's going to take heat. It's an endothermic reaction. But if you use the other definition, where you are actually forming it, energy is going to be released. So the table is going to match the definition. Stick with whatever your textbook uses in here. Okay? Pretty much this is all you're going to be doing. We're not going to waste too much time with ionic bonds. You will in the lab. Is an interesting thing to compare when you dissolve them, because depending how strong the solution is, we're not going to get to all of that, don't worry. Just know the definition of lattice energy, and please use the definition from your book. This is the most common one, but it's not the only one. And it's one of those cases that you wish the UPAC could say, we are all going to use the same definition. As far as I know, the UPAC has never even tried to do that, okay? So these problems, like I said, they're not difficult, but there's many places where you can make a mistake. Work slowly. Make sure you're looking at the right molecule, at the right bond, okay? But I have worksheets with plenty of examples that you can practice. Make every mistake you're ever going to make before it's going to get graded. So this is one of the chapters where I very strongly recommend that you go to my Watson account, make an appointment, and practice. Because that's the only way that you're going to get this right. Okay? The more you practice, the better you'll be at it. And once it clicks, then you realize that, oh, that was easy. Yeah, but it first needs to click. And that clicking comes from practice. So I have plenty of worksheets for you to practice if you just make an appointment with me through Wisant.